So this is Newton's second and third law notes, part 2, and we're specifically looking here at Newton's third law. So Newton's third law is called action and reaction. So for every action, there is an equal, meaning same magnitude of force, and opposite, talking about the direction of the force, reaction. So, for example, we talk about if I push the wall pushes me. Here, talking about force, if I push forward being the direction, on a door with a force of 2 newtons, the door pushes backwards on me with a force of 2 newtons, or negative 2 newtons if you want to talk about direction. Here again, we're seeing the negative meaning the direction. And so we have seen a lot of these examples. If you remember back to the Newton's Law video with the Disney stuff, they were paddling a boat, and he said as the oar pushes backwards on the water pushes forwards on the oar. The more backwards pushing you're doing, the more forwards pushing the water does, and so the more forward you go. Swimming works exactly the same way. If you want to swim faster, push more water back, because then more water can push you forward. That's how swimming works. Same with walking. If I want to push backwards on the floor more, the floor will push me forwards more. I will go faster. And so this is pretty obvious to see. One of the things to keep in mind is that it is an interaction between two objects. So, for example, if I push the door and the door opens and hits somebody in the face, that's not action-reaction. Action-reaction is I hit the door hits or pushes on me. Another set would be the door swings open and hits someone in the face. That person's face also hits the door. So that would be 2 action-reaction pairs. But then we also see it with sort of odder things. So if I'm driving along and I hit a bug with my car with a force of 100 newtons, that means the bug actually hits me with a backwards force of 100 newtons. And that can be a little hard to really see. Like, I think we all get, I hit the wall hits me. But now we have 2 things that are very different and end up with very different outcomes. Although, realistically, me hitting the wall and the wall hitting me also have different outcomes. This goes back to that question we asked in the pretest about if you drop a ball to earth, meaning you're standing here, you drop a ball into the floor, the earth pulls the ball down, but the ball also pulls the earth up, and they're pulling on each other, according to Newton's third law, with the same amount of force. And so, in order to really understand that, what we have to do is bring in Newton's second law again. So, to truly understand what's going on here, we need to look at the interaction between Newton's second and third law. And that is specifically Chapter 4, Section 4 in your book. Chapter 4 in general is Newton's third law. Chapter 3 is Newton's second law. So, Newton's second law explains the differences in acceleration with similar forces. It talks about how the same force can cause 2 different accelerations, which makes all the sense in the world. We've already talked about it tonight with the tennis balls, that with the same force, a lead-filled tennis ball and a regular tennis ball are going to have different accelerations. That made a lot of sense. What we're looking at here, though, is not me giving a force to one tennis ball and me giving a force to the other tennis ball. It's me giving a force to one tennis ball and the tennis ball giving the same force to me. And remember, we've talked about pushes and pulls and things like that. Don't get confused and say, well, a ball can't pull something it doesn't have hands, or a ball can't push something it's not human, or it's not an animal. Or when we're talking push and pull, we're saying exerting a force, and a ball certainly can exert a force on another object, whether that object is a car, if you throw a ball into a car window, or a person, or whatever. So let's take the example that I just gave. A bug and I hit each other with 100 newtons of force in opposite directions. That's Newton's third law, and that's just what it is. The force of an interaction is always equal and always in opposite directions. So let's break this down. Let's look at what we know. We know that the force on the bug and the force on the car are both 100 newtons. We also know that the mass of the bug, let's say this bug is 1 gram, which would be about the mass of a paperclip. Quite frankly, that's probably generous. That would be a pretty big bug, but let's make the math easy here. So we're going to say 1 gram, which is 0.001 kilograms. And as we calculated in the Newton's second law video, let's say a 2-ton car has a mass of 1,818 kilograms. So now let's bring in Newton's second law. Newton's second law we know is F equals ma. And what we can do with that is we can actually rearrange it. We can solve for acceleration. We have the force, we have the mass, let's solve for the acceleration. So we can divide both sides by m, and that will cancel out the m. Or, here, let me do it this way. Let's divide both sides by m. Drawing with my mouse here, so it's not the easiest thing. And so now our m's cancel. And we get force divided by mass equals acceleration. And so when we actually do that, when we do 100 divided by 0.001 and 100 divided by 1,818, well, actually pause the video and you go ahead and do it, see what you get. You get the acceleration on the bug is 100,000 meters per second squared, and the acceleration on the car is 0.055 meters per second squared. Pretty close to zero, meaning the car is going to keep doing pretty much what it was doing before, whereas the bug is going to experience a huge acceleration due to the fact that it's got such a small mass. And so now imagine this on an even more extreme scale where we're talking about a tennis ball in the Earth. The Earth is so much more massive, I mean billions of times more massive than the tennis ball, that the resulting acceleration from the same force is so small, it's negligible. The Earth keeps on doing what it's doing. Acceleration is almost zero, meaning it stays doing what it's doing. There's not a net force on it to cause it to move. But that acceleration on the tennis ball is great enough that you see an acceleration. Not only do you see it fall to the ground, but it speeds up as it is doing so. It clearly has a net force on it. So this is how really understanding Newton's second law, which I think is the hardest to truly understand, helps explain some of the weirdness you see in Newton's third law. So go ahead and make sure you ask any questions that you have on the comment section, or certainly email, but the comment section is better because then I can answer there. Because not only will we have a pop quiz, but we're going to have a voter egg to see who doesn't understand this and maybe needs a little extra practice. Have a good night.